Okay, let's see. Are we? Yeah. Okay, everything's good. All right. So last time, here's where we were. We were talking about. Welcome back, everybody. I hope everybody had a good break. So yeah, last time we were talking about how to slice up solids when trying to convert a triple integral into a triple iterated integral, and we went through this process. I'm going to kind of remind you of some of this process. I'm going to go through it quickly since we've done it once before. But arbitrarily, we're going to slice first perpendicular to the x-axis. Perpendicular meaning, in this case, something kind of like that. That gives cross-sections that look sort of like this. The first of which is over here, which will determine your lower bound. And the last of which is, let's say, here, which will determine your upper bound. So there's where your outer bounds come from. We then fix a value of this outer variable. So we're going to fix x. Be looking at a single value of x. Therefore, looking just at this cross section. Don't worry about points in your solid that correspond to different values of x. We'll get them. X will range over all of these values between x1 and x2. Right? But we need to know how the inner bounds depend on x, how they are functions of x. So we look only at that value of x, arbitrary value of x, and then we start looking for the range of values of y slices, perpendicular to the y-axis. And those, if you think about what does a slice of a slice look like, something kind of like that, right? And again, with the first and last, the first being something like that, the last being something like this, and that will give you your y1 and y2, which, as promised, are functions of x, as they should be. We want to know how these y bounds vary as x varies. Okay. And then lastly, given a fixed value of x and also a fixed value of y, and looking only at this y slice of our x slice, right? And trying to understand the range of values now of z. Well, z is going to start at whatever the value of z is that corresponds to that first point, and it ends at, whatever this z value is at this last point, right? So it's a slice, the slice of the slice, right? It's sort of a three-step slicing process. So some things to recall. Notice that we do have a language issue, right? How do we refer to the different integrals and the different, how depending on how we order the differentials? And watch out for terms like first, because the one that is first in the slicing process is not the same as the one that is first in the cranking it out process, right? You got to be real careful about that language. So I like to use outside and inside for the obvious differentials there, and then the one that remains, you can call it middle, or conveniently, you can call it second, and no misinterpretation possible because it's second in both senses. Okay. All right. Furthermore, notice that for any given one of these integrals, let's look, for example, at this inside integral, the dz integral. Couple things to say about it. For one thing, the bounds, right, the z bounds, notice they are functions of the outside variables. Right? Again, as they should be. The whole idea is I want to know how these z-bounds depend on those values of x and y. Right? Furthermore, related, keep in mind that while we are doing this inside integral, those outside variables, further to the outside variables, are treated as constants. Okay, so all very sort of reminiscent of double integrals, analogous observations and interpretations we made for double integrals. Okay, all right, and with all of that noted, we are going to now dive in and start doing some examples, and I'll comment as we go along about certain interpretations you can take. Okay, so we're going to start with this tetrahedron example. We have an integral defined on this tetrahedron. I'll remind you that, why do we have an integral on a tetrahedron? Oh, I don't know. Could be any of a million different things, right? Maybe I want to compute how much mass is inside of here, or maybe this is a oddly shaped aquarium, and I want to compute the amount of algae growing in the water or something, right? There's any number of different things that can accumulate over a solid region like this. So we're not going to worry about where this triple integral came from. What we're focused on here now is going to be, how do I turn a triple integral that I've written down for whatever reason, how do I turn that into an iterated integral that I can then sort of crank out? All right, so following our process, starting with the outside differential, dx. By the way, why did I put them in this order? No particular reason. I've got 6 options. This is as good as any other. Okay. This won't always be the case. Sometimes it will really matter. Sometimes the order of the differentials is a really big deal, and we're going to see some examples of that in a few minutes. Okay, so x. What's our range of values for x? Well, there's my x-axis. My first x slice is like that. My last x slice is some point there, let's say about like that. And what are the values of x at these points? Well, I think the first one is kind of a freebie. X is sort of obviously 0 on that first x slice. And I'm going to say just because of the geometry of the picture, right? Or if you prefer, I could observe that first slice is literally inside of that plane where the equation was given. So it's pretty clear. Everybody happy? All right, so what we're going to focus on now is the the last value of x. Where does that upper bound for x come from? And again, that's this point right here. How do I turn that point into a value of x? What I have to do is indicate what can I tell from the picture that I know geometrically about this point. Then I have to, so what surfaces is this point on? Then I have to ask, what are the equations for those surfaces? And then I solve for x because that's the variable I'm interested in. Okay, so here we go. Let's see here. The first thing I'll notice about this point is it is on that face of my tetrahedron. How do I know that? Picture, right? The picture tells the story. It's actually pretty hard to make an algebraic case for this kind of thing. You really need the picture to be able to look at and see where on my object is my last x slice, and geometrically what can I see about which faces it's on. Right? So don't try to come up with an algebraic version of this. It doesn't work. It might get the right answer a curiously high fraction of the time, but it will not always get right answers, and it therefore is not good reasoning. Right? And keep in mind, this is not about answers. If you coincidentally get a right answer, it's not the point. Right? We're looking for good reasoning. Okay. So the picture tells me that that point I'm interested in is on that face, which has that equation. Now, the picture also tells me that's on that face. Right there in the picture. Again, I got to have a picture to make sense out of it. It has that equation. And then lastly, got to rely on the picture here. It's on that face, which has that equation. So, knowing as I do that the point I'm looking to understand satisfies all 3 of these equations, and keeping in mind that why are we here? What's the purpose of studying this point? What does it tell me? I'm trying to figure out an upper bound for x, right? So I'm going to be looking to solve for x in this little trio of equations, and solving for x gives me that, which is my upper bound for x. Everybody happy? All right. Okay. Now, per our process, we're going to fix x. We're going to look at just at this single x slice. We're going to move on now and look at y. So I want to know what's the range of values of y here. Okay, well, y slices start here and end there. So, all right. So again, sometimes you get lucky. The starting value for y is, I'm going to say, obviously 0. That, after all, that first y slice is in the plane y equals 0, right? So it was a freebie. You get lucky sometimes, and that's nice. The last one, the upper bound for y. I need to understand this point. And now again, this is one that's not immediately obvious. You got to think it through, and you got to rely heavily on the picture to be able to make the following case. What do we know about that point? First, I know that it's on my selected x slice, right? So now I like to write that down with this silly equation, x equals x. That's just my little sloppy way of indicating, if only as a reminder to myself that I know what x is given. And so that is something that I'm going to be relying on. My answer here will depend on x, and of course you can cheat ahead and see that that's going to bear out. Okay. What else do I know? I know that this point is on this face, thank you, picture, which has that equation. And I also know that the point in question, again, keep in mind that blue point, it's on that orange face, which has that equation there. So again, what am I interested in? The whole point of all this is I'm trying to find a y bound. So for this point that's going to tell me my y bound, I need to solve for y. And I get that for my upper bound. Everybody okay? Yeah.
Can you explain why x from the picture?
Yeah, so that's right. So the idea is that we know what the range of values of x is, right? And we're now interested in knowing the range of values of y, but in particular, I need to know what the range of values of y is just for one value of x at a time. And so I need to take x as a given, right? My answer is going to be dependent on x. And with that in mind, I need to, proceed with what else I know about that point. Does that make sense?
So you're saying that y2 is on...
I'm saying what now?
You're saying that y2 is at a given x value?
Well, y2 is a function of x, right? So let's go back to this right here, right? So if slicing in this order as I am, right? My y bounds are functions of the outer variable x. Yeah. Okay. Yes.
Why is the z2 that you're solving, are you arbitrarily picking your x2, y2, and z2 points?
Oh no, it's not. No, these are what the bounds are for those integrals given the shape of this domain, right? So this y2 right here. Oh, whoopsie, wrong color. This y2 that I just solved for right here. What that is, that's telling me what the value of y is at that point. In other words, for a given value of x, given a green slice here, y stops at that point. And that's just intrinsic to the shape of the domain there.
I think I understand that. For me, it's just for x2, you have y equals 0 and z equals 0, because at that point x2, y and z will always be 0, but at certain points along x, y and z aren't 0. But I get that at this point. Does it not matter?
I'm not really understanding your question.
Along the x-axis, as x is increasing from
Yes.
0 to x2,
Yes.
y and z are not always 0.
We haven't even gotten to z yet, right? What we're interested in for the moment is we're trying to figure out what's the range of values for y. Here, let me clean up the picture just a bit. Right? Oops, picture. Here we go. Okay, so we've already figured out x, right? So x is going to range from there to there, for each value of which the range of values for y is going to change pretty dramatically, right? So for lower values of x up here, the range of values for y is a lot.
So
For greater values of x, the range of values of y is less. And I need to know, in order to sort of document the shape of the domain, I need to know how those y bounds depend on x.
which is where the y2 comes in?
Yes.
Okay, so then when you're writing the equations for like x2, y2, and z2, are those your final points? Like,
Are they what now?
like y, like.
Maybe let's
y-
talk after
yeah.
class.
Okay.
Yeah. Okay. Yeah. Okay. Okay. All right. Okay, so let's see. So we've got a range of values of x. X goes from 0 to 1 like so. We've just discussed how y, for a given value of x, has a certain range of values. And, of course, that depends on what the x is. For different x's, we'll have a different range of values of y. Now, what we're going to do now is we're going to continue to view x as fixed, focusing our attention on this x slice. We are further now going to fix a value of y. We're going to take y as being fixed. So we're going to look at now this y slice of our x slice. And only on that y slice of this x slice, we now want to know what's the range of values of, let's see here, of z. And z, here just for color coordination purposes, I'm going to do it like this. Z is going to range over that little vertical line segment, right? Let's talk about what is the lowest value of z. Well, the lowest value of z is it's going to come from that point right there, which is in the xy plane. That's where z is 0. So for this domain, it's kind of a freebie that the lower value of z is 0. Now the upper value of z is going to come from this point. And again, we have to think, what do we know about these points, right? What do I know about that point that's going to define my z2? And I know 3 things. I know what x is. We're on our x slice. We're trying to see how this z bound will depend on, among other things, x. Likewise, we know y, right? And the last thing that we know about that point that determines our upper value of z, and again, you got to rely on the picture for this kind of thing. I know that that point is on that plane that has that equation. Yes?
So for x, do you use the, I guess, like the predetermined, like x equals x from y2? Because it looks like that one segment is like fixed along the x-axis. Like it's not changing, if that makes sense. So like, are you just using x equals x from what you saw for y2?
I'm sorry. I'm not understanding the question. So once we fix a value of x, once we've done our x slicing, right? Then we have to fix a value of x. X doesn't change now for the whole rest of the problem, right? So the point being, if you look back up at this sort of generic example here, right? We're trying to see, again, I will get to all of those values of x, right? The question isn't what is the overall range of values of y, because I don't care about that. What I care about is for any given x, what's the range of values of y? And in particular, I want to know how the y bounds depend on x. So in particular, how the y bounds are functions of x. And if you want to know how something's a function of something else, you got to pick a value of that thing you want to be a function of. Does that make sense?
Yes.
Okay, cool. All right. So, again, we're trying to find now our upper bound for z, that point about which I know these things. Interested in finding a bound for z, so I need to solve for z. And I get that, a little bit of algebra there, and that tells me my z upper bound. Yes?
So is there a reason that you started with x as your, like...
no particular reason. Yeah, I have 6 different options of how to order these differentials. Just to get the ball rolling, I picked one.
Like in this case, one of them wouldn't necessarily be easier than the other, right?
Yeah, that's right. This is highly symmetric, so yeah, that's right. You got a lot of options here. I'm going to show you some. My next examples won't be as friendly.
Okay.
Yeah, right. Yes.
For the upper bound of Z, why did you choose like that middle point and not like the top of the triangle?
Right. So I'm not interested. So you got to keep in mind what these bounds mean. Right. So let's look at this equation or this setup right here. Right. This does not mean what is the greatest value of Z on our domain. Right? It's not what it is. This is the greatest value of Z for a given X and a given Y. I need to know how those bounds depend on X and Y because it's going to change. Right? I mean, for different X's, different Y's, I'm going to have different slices and different slices of slices. It's going to look totally different. And I need to know how it depends on those outside variables, X and Y in this case. So I mean, yeah, it is true that, maybe there's a value of Z way up here, right? That's maybe greater than the value of Z at this point. Well, that's fine, right? But this is not the question. Right? What we're interested in is, for a given value of X and Y, I just want to know how much domain is there sitting above that value of X, that value of Y. And this is what that is, right? Some point over here just isn't what I'm looking for. It doesn't get at the shape of the domain. Does that make sense?
Yeah, so it's for like a specific point, X, Y.
Yeah, that's right, exactly. So how my Z bounds are functions of X and Y. Yeah, how they depend on X and Y. That's right. Okay. So so we've made it through this first example here, and let's see here all together then. Notice, as promised, my Z bounds are functions of X and Y, and that's okay. That's how it's sort of expected to be. And then likewise, notice that my Y bounds, right, expected to be and are function a function of X. Okay. All right. Okay. Okay. So yeah, we had 6 different choices of how to order our differentials. I picked this one arbitrarily because for this nice, easy starter example, it doesn't really matter. Suit yourself. I just picked this out of a hat. Right? It won't always not matter. Sometimes it matters quite a bit. And hard to draw pictures to justify, but I'm going to say that the same rules that guided us on this for double integrals also apply for triple integrals. Try not to slice through corners. All right, bad things will happen. And then also, whichever variable you would rather solve for, put that on the inside. Right? Because you're going to have to solve for it if it's on the inside. And that will prevent you from, unfortunately, having to solve for something you don't want to have to solve for. Okay, this last business here about projections really makes a lot more sense in context. So I'm going to momentarily skip this. I'm going to come back to it in just a minute. I want to kind of dive in to this example, and we'll see it play out inside of this example, and then I'll go back and refer to it. Okay, so here we go. We have a region defined by blah, 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 and this is what the picture looks like. And it's a hard picture to draw. You will recall from the last example that having a good picture is really important. And this one's hard to draw, so it becomes natural that in order to be able to make a good analysis of these kinds of questions, you really do need to have a good picture. You really do need to be able to draw reasonably well. I know that most people in this class haven't had a lot of practice with that kind of thing. So I encourage that you try to develop your skills with drawing. I have a couple of videos on my YouTube channel that I hope are helpful. This everything that I know about mathematical drawing, and I think it's good tools that'll help you all with the drawing process. Okay. All right. Okay, so following the rules on the previous page, I look at this equation right here. I see z as very naturally being a function of x and y. All else being equal, rather solve for z. For one thing, it's already done. More importantly, it's the only one I can solve for without square roots. Right? So I have a pretty strong preference to put z then. Oh, whoops. Put the z integral on the inside. Does that make sense? All right. Now that suggests process of elimination that x and y have to be the outside differentials. And I'm going to claim that this means that we're looking at a projection to the xy plane. Now, I've got to explain what this means here. And I claim it's going to be a good projection into the xy plane. What we mean by a projection is if you take your solid and just look at the shadow in that coordinate plane, right? So looking at our original solid, its shadow is this quarter disk, like this. Okay, so what makes this a good projection? And I got to come back up here and think through the steps. It says here, first thing, the shadow needs to be desirable. And what I mean by desirable is it needs to be not that bad. It can't be anything, let's say whatever shape that is, you're going to have to do an integral on it, and you don't want that to be weird. Right? So a quarter disk, all else being equal, I'd prefer a rectangle, right? But it's not that bad in the big scheme of things. Okay. All right. What do I mean by top and bottom surfaces, and what do I mean by them being consistent and desirable? Let me address that now. We're going to come down to here with my x and y on the outside, right? We know that when it comes time to finding my range of values for z, z is going to range from somewhere to somewhere as, 4 given values of x and y. We will have picked an x, or I guess what got y on the outside. We will have picked a y, we will have looked at the y slice, we will then pick an x, and then the range of values for z will be something like that. So what do I mean by the bottom surface? Well, this point that determines the lower value for z, that point's always on that surface right there. It's always on this paraboloid. It's always on that blue surface. And I'm going to say this is what I mean by consistent for every x and y in the projection. Every value of x and y. It's consistently always this blue surface that holds the point that determines my lower bound for z. Right? And then likewise, the upper value for z, where is that going to come from? Well, that comes from, this point, which is consistently on that surface. Z equals 1. Every value of x and y, that red point is always on the same plane. All right, is that cool? So that's what I mean by consistent, and by desirable, I just mean that when you solve for z in these equations, that again, just keep in mind whatever you end up with is something you're going to have to deal with. And again, everybody prefers constants. And hey, look at this, one of them is a constant. That's nice. This other one, oh well, it'd be nice if it was a constant, but at least it's just a polynomial. It's not that bad. Okay. All right. Now, so what? What's the big win here? Why are we interested in making this sort of point of view of a projection? And there really is a great payoff here. Here's the payoff. If you look at your original solid, and if you look at the projection down here, the solid and the projection will have the exact same x bounds and the exact same y bounds. And why is that valuable? Well, because this original solid's really hard to draw. And drawing a slice, let's say as I have drawn here, a slice perpendicular to the y-axis, really hard to draw. And it's so much easier instead to be able to say, I don't have to deal with maybe my picture of this is not great, and I don't want to spend the time it would take to make a good picture of it. No problem. All I have to do is draw the shadow. Just draw just the projection. And you can use just the projection here to figure out what the bounds are for your projection variables, your outside two variables, x and y in this case. And that analysis is actually a lot easier. Again, no ugly slices to draw. It's just look at a quarter disk in the xy plane. How we doing? Everybody okay? Yeah.
So are you saying are they step 1 and step 2, or is that just two different ways to look at it?
Yeah, two different ways. Two different motivations that conveniently, fingers crossed, thankfully it worked out in this case, that my two different motivations happen to motivate the same ordering of the differentials. Yeah. So item 1 up here motivates putting dz on the inside. Item 2 motivates putting x and y on the outside. And so thankfully, same. Yeah. Okay. All right. I think this projection trick is a really nice trick. I think it's underappreciated. I think it's undersold in most multivariable calculus textbooks. And it turns hard problems into relatively easy problems. And again, in this case, really hard to draw this solid, but a quarter disk is easy to draw. It's the equation of a circle. There's not that much to it, and easy to find these bounds. Just like, by the way, you were doing literally a double integral in the xy plane over that shadow. Okay. All right. Now, with that in mind, it remains. We still got to figure out what's the range of values of z. Right? If we look over, for example, a point like this, for a given value of y and a given value of x, I need to know where does z start, where does z end. Well, again, I rigged it up so that, right, I chose to do the projection in this direction so that this point defining the lower z bound would always be on the same surface, which is then easy to solve for. Right? And likewise, the upper bound for z is going to come from this point, which is always consistently on this upper face, which has easy to solve for z. And again, answer there. Everybody with me? Yeah.
So you kind of just arbitrarily pick the order that you're doing x and y because it's the same.
Oh, yeah. That's right. There's a lot of symmetries down here. No, that's right. I could have done dy dx instead of dx dy. I just did it in this order just to mix it up, frankly, from the previous example. In this case, really doesn't matter which way you do the x and y. Yeah. Okay.
So when you projected, you can't really use the same trick as you did last time because z isn't really 0. You know what I mean? Like when you were finding your y bounds, even though you projected it onto the xy plane, you can't do it from the previous example where you say 0, 0.
Oh, yeah. Well, no, that's right. The lower bounds being 0, this is not a general thing, right? This is because the shape of our solid, it just happens to be that those lower bounds are 0. That's just a lucky break. Yeah. No, in all cases, you have to look at the picture and see literally where do they start, where do they end. And in this case, z starts way up here. There is no solid down here, right? And so the range of values of z is from here to here. Yeah. Is that cool? Yeah. All right. Here's another example. Now again, you can slice, and then slice the slice, and then slice the slice of the slice if you want. It's hard to draw. It's surprisingly hard to draw. And you may be thinking, it's a ball, for crying out loud. How hard could that be to draw? Right? A ball is, round. Right? Easy to draw. But drawing the slices and the slices of the slices, surprisingly challenging in my experience. So now this is an attempt at that, the way I have it drawn here. An attempt to sort of slice the slice and all that. Let me show you what I think is the easier approach on this. Arbitrarily, I'm doing my differentials in this order with dz and dx on the outside. I can view this then as relating to a projection in the xz direction. Right, and I can look at this xz projection here. That's a disk. Nothing to. I don't even really have to draw there exactly because I know what the unit disk in the xz plane looks like. I can draw it on the side somewhere, and that's a fairly straightforward double integral question. So these bounds right here for the dx outer integral and the dz middle integral, I don't really even need the three-dimensional picture. Right? And we're 2/3 of the way in, right? And we haven't really even done anything artistically challenging yet. It's a nice win. Okay, now let's think about the range of values of y, right? Our inside variable. Well, y for any given x and z is going to do something kind of like this, right? You know, for a given x and for a given z. Okay, well, let's see here. This lower point, this point at sort of the starting point, if you will, that determines the lower bound for y, it's always on, missed. It's always on that back face of the sphere. You can write down the equation for that. You can solve for y on this purple surface. Keep in mind, the purple surface is on the negative y side of the xz plane. So when you solve for y for the purposes of finding this purple point, you choose the negative square root. On the other hand, which by the way then gives you that lower bound for y. The upper bound for y is going to come from this point over here on the other side, which is always on this hemisphere. Right, the dark blue hemisphere. Which again, you can write down the equation, you can solve for y. Notice that on this dark blue side, y is always positive. So you pick the positive square root there, and that gives you that upper bound for y. And so there you go. I think that if only artistically, this is quite a bit easier than trying to draw the slices. Everybody all right? Yep.
So to clarify, for the y segment, you're setting, or you're isolating y, and then you're setting it, and then you're not fixing any variables.
X and z are both fixed. Yeah.
X and Z.
Yeah. So for given values of x and z, in other words, we're going to assume that we're looking at some specific point. That doesn't show up very well. Let me do it like this. For some specific point in that green disk, right? And then you look at the range of values of y corresponding to that point in the green disk. So x and z are fixed. The outside variables are always fixed when you're thinking about the inside variables. Yeah. Is that cool?
Yeah.
Okay. All right. Okay. This is a nice example. A little bit weird. There's an artistic challenge in this one. I want to show you. I want to first try to persuade you how hard the artistic challenge is, and then I'm going to show you the workaround that makes it not so bad. Here's what's hard about it. We've got 5 planes here, and in general, if you have 5 random, every plane coming in at some weird angle, 5 planes, and you want to know how those planes intersect and what's the region that's bounded by those 5 planes, is very, very difficult in general. Right? So at a glance, this looks really, really hard. The foot in the door, the thing that makes this doable, is I can observe that 3 of these equations have no y's in them. This is really nice to observe. And flashback to chapter 1, if there's no y's in your equation, the result has got to be parallel to the y-axis, because you can change the value of y and nothing happens, right? So these three planes here are all parallel to the y-axis. So once you know that they're parallel to the y-axis, I can just say, all right, well, let me just kind of focus my attention in the xz plane for just a moment. We'll deal with the y direction just in a second. But looking just in the xz plane, I mean, z equals 0 is just this right here, and z equals x is just something like that, and x plus z equals 2 is about like that. So I've got three planes parallel to the y-axis, and they look like this when they intersect the xz plane. So they're just going to be all together kind of like this. Is that cool? So we've drawn 60% of our picture, and again, we haven't had to really artistically exert yet. Question.
Sorry, can you explain how we got the triangle shape again?
Oh yeah, so just looking just within this plane right here, and just asking what do these things look like in that plane. Just kind of get the ball rolling, right? So what I've got inside of this purple plane is just kind of a foot in the door partial picture. But the thing is, if I've got a plane who intersects this coordinate plane like that, but I also know that it's parallel to the y-axis, then again I can just kind of drag parallel to the y-axis and that'll sweep out that plane.
Okay.
Yeah. Okay. All right. So the last two planes are just a kind of matter of writing them down. Let's see here. Y equals 0. That's this. Right. The last one's annoying, but it's got to be done. X plus y plus z equals 3 is a great big plane, kind of like that or something. And now you have to use your sort of geometric imagination of, we've got this prism, this green prism like this, and then we've got a plane kind of cutting through at an angle, right? And so, if you'd like, right, if it would help you to visualize what this looks like, you can literally solve for these 3 points, right, to see exactly where those are. That'll guide you in where to draw those corners, and then that'll help you draw this face here. That is how this last plane sort of shows up in the picture. Everybody good? Okay. Okay, so what do we do with this shape? Now that we have a reasonably decent picture of the shape, again, you can start slicing if you like. The slicing process is going to have problems in all but one way. And now this is a really good exercise, a good little mathematical, exercise to try the 6 different orders of slicing. Just try all 6 of them. It's a good exercise in drawing as well, right? And for example, as you slice, you'll notice that perpendicular to the x-axis, your slices are hard to draw. This is not a great drawing, but anyway, there's a slice perpendicular to the x-axis, and those slices continue to look kind of like that until you hit this corner. It's kind of an edge, right? But it's got, among other things, a couple of corners on it. And when you hit that, all of a sudden after that, your slices look different, right? Your slices now kind of like that. And remember, one of our rules is try not to slice through corners. So, bad choice here. Right, so try another one, right? And again, I encourage you to go through all 6 and convince yourself that you're going to hit a corner in 5 of those 6 possible slicing orders. And the one exception, the one way in which you don't hit a corner, is this one. So if you're going to do an integral on this solid, you really should do the differentials in that order right there. Is that cool? Everybody? Yeah.
If you were to slice through Z,
Huh?
why are there no corners?
Yeah, okay, so Z slices. Yeah, Z slices look kind of like that.
Yeah.
Right? Now, I do hit corners down here where z equals 0, but the thing is I was going to start a new integral there anyway, so who cares, right? And I will also hit corners up here, but I was done already anyway, so having to end an integral's cool. I was going to end it anyway.
Oh, so that's why you put Z on the outside?
That's why what?
That's why you would put Z on like that.
Yep, that's why it's okay to put z on the outside. That's right.
Okay, so in terms of figuring out how you want to slice stuff, like, obviously you don't really want to go through all 6 possibilities.
Well, that's right. So I have a better suggestion. Nevertheless, I do think that yes, you should go through all 6 possibilities. I know it's painful, right? But it's a good. The more you go through tediously, painfully drawing, the more you'll kind of develop a geometric sort of instinct, and you'll kind of be able to see it coming without actually having to draw the picture. And so, like, I can look at this picture and just think, all right, my slices, now I'm going to hit corners there. No, I'm going to hit corners this other way, and I'm going to hit that corner going this other way. You can just kind of see it happening, and actually doing that will build you up to being good at doing that in your head. Yeah. Yes.
Why would dx dy dz not work?
Which one?
Dx dy dz.
Oh, yeah. Okay, so you've got dz on the outside, just like we have here. Whoops, let me do this, and let me get rid of my mess here. And so now let's talk about doing dy next, right? Slicing perpendicular to the y-axis. At y-axis, my slices look like this. And I hit this corner right there, on the other side of which you'll notice that there is a sort of a different thing happening to those y slices. You might say that the upper bound for x over here is determined by this surface, whereas on the other side of the red point, on the other side of that red corner, the upper bound for x is determined by that surface. On sort of that edge. Is that cool? Yeah.
So if you can't split it up so that you don't hit corners while slicing, do you have to just do like addition of 2?
Yeah, that's right. Sometimes life is mean and there is no way to avoid corners, and you have to break it up into 2 separate intervals. Yep. Harsh reality. Yeah.
Why can't we do dy, dz, dx?
Oh yeah, that one fails immediately because if you want to put dx on the outside, right, your x slices look like this. Terrible. But the point is, you will hit this corner as those slices move along. In particular, once you get to this value of x, you're going to hit that corner. Does that make sense? Okay, now let me show you the better way, I think. And as y'all have noticed, I've been pushing this idea of projections, right? Look for a good projection. And I think there's a really good projection staring us in the face. Let me start by showing you what a bad projection could look like. Let's project down into the xy plane. Let's just see why is this bad? Well, if I project down into the xy plane and ask what is the range of values of z, like that. What's the range of values of z? Well, my lower bound for z is always going to be on that surface, and that's fine. But my upper bound for z is going to be on this face for some values of x and y, but it'll be on this face back here for other values of x and y. Right, so this is what I would call a bad projection. My upper bound for z, my upper bound for z is, depending on where I am down here, it's on 2 different surfaces. We don't want that, right? This is a bad projection. The good projection, again, it's a healthy exercise to kind of just think geometrically about, well, what are my options and which way does it go? I think the best one is like this, where we project in the XZ direction. For which purpose, if I look for how Y ranges, right? Notice that my lower bound is always on that surface, no problem. And my upper bound is always on this surface, no problem. Right? So again, this is a different way to motivate the same choice for your differentials. You get the same answer, right? But I feel like maybe a little bit easier to see geometrically. Is that cool? Everybody happy? Okay, good exercise to fill in the blanks here. Make sure you're comfortable with this order of the differentials. So there is one last example here that, let's see, we just don't have time for, I'm sorry to say. I'm just going to point out, though, that this one, it's really bad to do slicings of this. This solid here is very, very weird and ugly and hard to draw. But it has a very simple projection to the XZ plane. The lower bound for Y is always on that paraboloid, and the upper bound for Y is always on that paraboloid. So it actually is a pretty easy one to slice up if you take this point of view on projections. Take a look at those details. I'll see y'all later. Have a good rest of your Wednesday. See you on Friday.